Uh, Today we're working through the remainder pages of the packet. Um, we'll do some curve sketching. We'll review first derivative test, test for concavity, second derivative test, a particle motion, and then I would like for us to practice, at least show you, what calculator questions on multiple choice can look like in terms of, how they want you to use your calculator to find certain solutions. So number one, at what value of x does f of x have a relative minimum? So we're going to go through first derivative test. We're going to set f prime or find f prime, find critical points off f prime, populate our f prime sign line, and then look at the arrows, the positive and negative slopes. And then from there, we can decide, okay, where do we see where the slope is decreasing, followed by increasing, because then we're going to be able to find a relative minimum. Okay, so let's find f prime. Power rule. I find it easier to identify critical points if I can get my terms into one fraction, because then I can set my numerator and my denominator equal to 0 separately, because I know critical points can come from both the numerator and denominator of your derivative. So my common denominator, well, first off, the same thing as 1 over 1 minus 1 over 3x to the 1/3. My common denominator will just be 3x to the 1/3. I can balance each of the fractions here. My old denominator, I need to multiply at the bottom by 3x to the 1/3. So I'm going to balance the top by multiplying the top by that as well. The second term doesn't need to change. It's already the common denominator. So if I set the numerator equal to 0 and the denominator equal to 0, I'm going to find two critical points. Add 1, divide by 3. To get x by itself, I can cube both sides. And I get x equals 1 over 27. Here, divide by 3, I get x equals 0. So I have two critical points. They're both going to go onto my slope sign line. Oh, sorry. I lost something here. Sorry. Sorry, I lost this 2 here. I brought the 2 down, but I thought they were canceling out instead of multiplying. So 4/3. ends up giving me 64 over 27 and 0. So my slope sign line, 0 and 64 over 27. I choose values in each subinterval to test. I'll test -1. I'll test 1. And 64 over 27 is greater than greater than 1, but less than 3. So if I test -1 into my derivative function, I'll get a negative over a negative, which is positive. I plug 1 into the derivative. 3 minus 4 is negative. Negative over a positive is negative. If I plug 3, I'll get 3 times cube root of 3. It's going to be slightly, slightly more than 4. So this is positive over a positive. So we can see that there's a relative max at 0, a relative minimum at 64 over 27 because of the slope behavior, right? Decreasing followed by increasing. We're going to get a valley of the graph, which we can say is a relative minimum. Okay, number 2, points of inflection. So points of inflection comes from the second derivative function. So we're going to do the same, a similar process as number 1. It's just that we're having to do everything at the second derivative level instead of the first derivative level. So we're going to find y prime, find y double prime, set y double prime equal to 0, find your critical points, populate your sign line, and then test your subinterval. So here's number 2. Okay, I'm just going through power rule twice. And I'm going to set my y double prime equal to 0, factor. I have 2 critical points here, 0 and 1, but are these guaranteed to be points of inflections? Can I just say that these are critical points and therefore points of inflection because these are where double prime is equal to 0? What do you guys think? Or do we need to do something more? Timeline. I want to point this out because a lot of students stop here because it feels like, well, I have my answer, so why don't I just go ahead and use it? It could be the case, but we want to make sure that if we're calling it points of inflection, there has to be a change in signs before we can call it points of inflection. I mean, right now, these are critical points. If there's no change in sign, then this critical point would remain a critical point, but it wouldn't be a point of inflection. So make sure that you take the time to actually test the sign line because it's possible that one of these may not have a sign change or both of these may not have sign changes. If that's the case, then we don't want to include that. So just be aware that this is a common mistake that students experience where they feel like, well, I've solved for X, so there's my answer. But points of inflection requires change in signs. So, but you know, it very well could be the case that these are points of inflection, but sometimes on the AP exam, they create situations where one of them may not be to see if students are actually testing their sign lines. So I'll test -1, I'll test 1/2, and I'll test 2. They all get inserted into the second derivative. Either one is fine. I like the factored form because it allows me to get to the signs a lot quicker rather than doing a bunch of calculations. So if I plug -1 in for x, I get -12 times -2. So 2 negatives makes positive, so concave up. Plug 1/2 in. 12 times 1/2 is positive. 1/2 minus 1 is negative. Positive times negative is negative. If I plug 2 in, positive times positive is positive. So in this case, both the critical points end up being points of inflection, but a lot of times I've seen enough problems where on the AP exam or on multiple choice section where one of them may not be a point of inflection because there's no change in sign. It ends up just being one of them. But in this case, both of these x values are points of inflection. So we have to plug them back into the original equation to get the full order pair. So I plug 0 into the original function, I get 0. I plug 1 into the original function, I get 1 minus 2, which is -1. So answer choice B. So this process I call test for concavity, but there's another test called second derivative test. And you may feel like, wait, shouldn't this be called the second derivative test, what we just did? Well, the name second derivative test is finding relative max, relative min. Second derivative test achieves the same goal as the first derivative test. They're both finding relative max, relative min. It's just that one is using first derivative and the other is using first and second derivative, so they call it second derivative test. But second derivative test is not what we just did. This is called the test for concavity. So how does it work? Second derivative test is where we're using slope and concavity to help us decide what's happening at that point. Is there a relative max or a relative min? Okay. So let's look at example 3 here. It says if f prime of 5 is equal to 0 and f double prime of 5 is equal to -3, I first want to point out is that these are talking about the same location on the graph, but they're giving us different information about the behavior of the graph. So when it says f prime of 5 is equal to 0, can you visually describe what's going on at this point? This means what? At x equals 5, what's happening at this point? There's a what? What is f prime equal to 0? What does that look like? What's another word for derivative? Slope, right? Slope is 0. Okay, so at x equals 5, my slope is 0. Right? Now, if this is the only thing given to you, you're not able to make a full conclusion because, I mean, slope zeros can be a flat, the graph flattening out. It could be a relative max, it could be a relative min. Any of these locations could end up being slope zeros, right? We don't know what's going on yet, right? Is it a relative min? Is it a neither? Is it a relative max? So we need more information. And more information is coming from this f double prime of 5. Now it's giving us more detail about the same point. And it's saying that f double prime of 5 is equal to -3. The number is not that important. It's the fact that it's what? What's important about second derivative? That this is what? I mean, it could be -3, it could be -5, it could be 27, it could be 2. We want to talk about what? Negative concavity, right? That means concave down. So the number is not that important. It's the fact that f double prime of 5 is less than 0. So if I pair those two informations together, I know it's got to be a slope 0, but then it's part of a concave down graph. So if something is part of a concave down graph, and that point is exhibiting a slope 0, then I must be looking at a what? Relative x, yeah. At x equals 5. So this is second derivative test. It's using two pairs of information, and it allows us to kind of pinpoint, okay, if you're giving me both behaviors about the same point, then it must be a graph that looks like this. Right? So I think some students get thrown off by the fact that, oh, they see a negative and they feel like negative is number smaller, and so they feel like it's like a point on the graph, and they would think that's a relative minimum. But this is not a point. This is a concavity. Right? Likewise, if I had f double prime of 7 is equal to 82, and f prime of 7 is equal to 0, I know that 82 may feel like, oh, that's a really high value, so that must be a relative max. But what does it tell us? This tells us that 82 is not that important. It's the fact that it's what? Positive. And so therefore, if we can verbalize this as concave up and visualize concave up, then we could be able to visually convince ourselves, oh, this is not a relative max, this is a relative minimum. Even though this number kind of throws us off a bit because it feels like a point it's not a physical point on the graph. This is describing a curvature of the graph. Okay. Next page. We're just going to review f prime graph. I think you guys have shown your ability to do that recently with our FRQ test. But if we're looking at the f prime graph, we know that anything above the x-axis is positive slope. Anything below the x-axis is negative slope. And then you can also create your second derivative sign line by picking off your max and mins. And then your decrease and increase will be your concavity. So see if you can create your slope and concavity sign lines, because once your sign lines are in front of you, then filling A through G is easy because you're just reading your information off of your slope and concavity sign line. Okay, try that. So for f prime sign line, you're looking at your x-intercepts. For f double prime sign line, you're looking at your relative max and mins. So my critical points, -2, 1, and 5, because those are my x-intercepts. Above is positive slope, below is negative slope. And then my concavity sign line, I'm just pulling them off of my relative max and relative mins. Those are my points of inflections. And then I look at my slope. Negative slope translates to concave down. Positive slope is concave up, concave down, concave up. Once you have all this in front of you, you can just read everything off of your sign line. Number 5, position of the particle moves along a line is given by S of t, for t greater than or equal to 0. So we're only looking at t values to the right of 0. For what values of t is the speed of the particle increasing? So increasing speed is where we compare signs between velocity and acceleration. So let's do this. Let's find velocity graph. Let's find acceleration graph. Let's create sign lines for both velocity and acceleration. Let's line everything up so that we can compare between velocity and acceleration. When are they going to have the same signs? Because increasing speed is if both velocity and acceleration are positive, or if they're both negative. So see if you can find your velocity function, find your set velocity equals 0, find your critical points, create identify your signs along your critical point, along your sign line, and do the same thing for acceleration. I'm testing my signs with my velocity function, factor form. So I'm trying to line up my velocity acceleration in a way where all the numbers are, where it's easy for me to see the times where they're going to share the same signs. So let's see, from 0 to 1, positive, from 0 to 4 is all negative. So these are not the same signs, but it does become same signs in this region, right? From 1 to 4. And then same signs again from 7 to infinity. Okay, so therefore, velocity and acceleration have same signs in the interval from 1 to 4 and 7 to infinity, and this is when speed is going to be increasing. Okay, I'll have you guys do page 15 on your own. Let's look at page 16. So this is a collection of some calculator type questions on the multiple choice section. Just want to show you what that can look like. Page 16, number 3. The first derivative function is given by f prime. So here's my f prime. What is the x coordinate of the point of inflection or the inflection point of the graph at f? So we know that point of inflection comes from the second derivative. So we can find the second derivative function, say equal to 0, and see where that takes us. So if I want to get to f double prime, I see how this is set up here. What rule would I need to use to get to f double prime? Product, right? Product rule. So f prime g plus f g prime. Now, this is going to be potentially tough to solve. You got x cubed. Even if we could factor e to the x out, this is not something that we can necessarily factor. But why don't we do this? Why don't we just graph this function? Since this is the calculator section, and just look for the x-intercept, right? Because if you're ever trying to solve an equation that's hard to do, and it's part of a calculator question, typically what that means is graph it and look for the x-intercept, right? That allows us to solve and find a solution graphically. And you're going to at least see a couple of those questions on the AP exam where they give you the calculator because they want you to use your graphing feature to find your solution. So I'm going to graph. Graph this and look for x-intercept. Right? When is this graph going to hit 0? I see a potential x-intercept here. I'm going to zoom in. So if I do zoom box, zoom in that region there. There's my x-intercept. I'm going to use second trace 0 to pick points on either side of the x-intercept and ask the calculator to find that decimal value for me. I got negative 3.196. Number 4. Let f be a twice differentiable function. That means it's a smooth curve. No sudden sharp turns, no holes, no asymptotes. F of 1 equals 7, f of 3 equals 12. If f prime of x is greater than 0, that means we're getting positive slope. And concave down. Which of the following is a possible value for f of 5? So I'm going to use table of values here. See if I can explore these order pairs a bit more. So I have order pair 1, 7. I have order pair 3, 12. And I'm looking for what could be a possible value at 5. Well, if my slope is positive, I know that 1, 7, 3, 12, 5, it's got to be a number that continues to grow, right? If I'm getting positive slope, I can't suddenly dip below 12 because then it's going to have to go down to hit that point. So we know that this number has to be greater than 12. But then at the same time, we know that the graph is concave down. What that means, concave down, is that even though the slope is increasing, the slope is, sorry, even though it's a positive slope, the slope is flattening out, right? It's becoming less steep, right? So that's what that means here. If I have a graph that's positive slope and concave down, the graph will look something, like this, right? Where initially it may be a slope that is, 3 or 4, but then it's going to flatten out to a slope that's less, right? So my slope should be decreasing. I mean, they're all positives, but it should become less steep if it's concave down. So if I find the slope between these 2 points here, my slope is 12 minus 7 over 3 minus 1, which is 5 over 2. What that means is this slope here has to be less than 5/2, right? Because my graph is going to do this. It's going to be a positive slope, but it's going to have to, if it's concave down, it's going to have to move towards 0. So given all these numbers here, all these numbers are greater than 12, so positive slope, but only one of these will allow us to actually create a slope that is less than 5/2. If I try 17, for instance, 17 minus 12 is 5. 5 over 2 is 5/2. I can't have a slope that's still 5/2, right? It's got to be something less. So let's try 16. 16 minus 12 over 5 minus 3, I get 4/2. 4/2 is less than 5/2. It's still a positive slope, but it's concave down because my graph is doing this. So my answer is 16. Number 6, a particle moves along the x-axis so that at any time t, its position is given by x sub t. What is the velocity of the particle when its acceleration is 0? So this is our first goal here. Let's find acceleration. Let's find when acceleration is 0. And then we can plug that t value into velocity to figure out the velocity. So I'm just going through and finding my equation at the acceleration level. It says when acceleration is 0, so I'm going to set acceleration equal to 0. But you can tell that this is not an easy equation to solve by hand. So that's why it's part of a calculator question. We're going to be graphing this and look to see when it actually hits 0. So graph and x-intercept. Okay. There's going to be at least a few of these on the AP exam where you're going to be graphing something and looking for the x-intercept and letting that be a part of your process of moving forward in the problem. So we always want to make sure that we're in radian mode, but ultimately radian mode, degree mode, that's only going to matter for trig. It's just safer if we always just have it set in radian mode, so we don't have to worry about, wait, when is it degree, when is it radian? It's just, yeah, but other than, if there's no trig involved, it doesn't matter if it's degrees or radians. So I'm going to do zoom 6. So I'm going to find the first instance when velocity is, when acceleration is 0. So let me zoom box here. Pick a point to the left of the x-intercept, hit enter. Pick a point on the other side of the x-intercept, hit enter. 0.729. So we know that acceleration is 0 when t is equal to 0.729. And then it's asking for the acceleration at this moment in time. So we'll just do v of 0.729 and just plug 0.729 in for a velocity function. And I get 3.696, which is answer choice D. Okay, your homework, the rest of the packet, 13 through 16. And tomorrow we'll start packet 3, which is for response, focus on for response topics on your AP exam. Can I come with your phones? Okay. Thank you. Thank you. Jackson, do you want to turn something into me or not yet?